Okay, welcome to our first Chapter 3 video for our Zane State Physics 2010 class. In Chapter 2, we looked at motion in one direction. So things were either moving side to side or up and down. In this chapter, we're looking at two-dimensional motion. So they're moving both side to side and up and down. And we introduced the idea of vectors in the last chapter. And as a reminder here, we've got Vector from Despicable Me. And he is, in the video where he is introduced, tells us that a vector is a mathematical quantity that has both magnitude and direction. And that turns out to be exactly right. That is what a vector is. And so we use vectors in physics class to describe things like displacement or motion, the way something is moving, velocity, how fast it's moving. Force is a vector because it has a direction associated with it and magnitude. Momentum, these are all things that have both direction and magnitude. And so, for instance, the car traveling here, its displacement, velocity, acceleration can all be described with vectors. How fast is it going and in what direction would be its velocity. So it's more than just simply its speed, but also its direction. So things that do not have a direction associated with it, that only have a magnitude, are called scalars. And some examples of scalar quantities are mass. Mass doesn't really have a direction. It only has a quantity or magnitude associated with it. Time really only moves in one direction. And temperature. You can't say that the temperature of something has a direction associated with it. It is what it is. It only has the magnitude. And in the last chapter, well, actually, I'm not sure if we really added vectors, but we'll look at that here. Adding vectors when they are collinear, when they are in the same direction or along the same line of action, is very simple. So the way we can graphically think about adding vectors is stacking them on top of each other, or arranging them from tip to tail. So if we start off here at 0, we have this 8-kilometer vector that goes to here. And then if we take the next vector and just tack it on to where this one ends, this one is 6 kilometers. And they're both going to the right along the x-axis in the east direction. And so when we add vectors together, essentially what we're doing is saying, okay, let's go from the starting point of the first vector to the ending point of the last vector and just go directly from start to end. What is that distance? Well, when they're aligned with each other, it's pretty easy. We just take, like in this example, 8 kilometers plus 6 kilometers, and that equals 14. So we just simply add them together, add those quantities together. Okay, the same is true even when the direction is different, so long as the line of action is the same. Both of these are horizontal vectors along the x-axis. This one is positive 8 going to the right. This one's negative 6 going back to the left. If we want to add these two together, we just take 8 plus a negative 6, and that's the same as just saying 8 minus 6, which equals 2. So the resultant of these two vectors is 2, and it's that simple. What is not so simple is when the vectors are not collinear. If we look at this example down here, we have two vectors d1 and d2. d1 is horizontal, d2 is vertical, so they're actually perpendicular to each other. But the idea is still the same. If we want to add them together, essentially what we're saying is, okay, if we start here at the starting point of the first one, and we end here at the ending point of the last one, and instead of following that path all the way to the right and up, if we just go directly from the starting to ending point in the most straightforward fashion, as the crow flies, as they say, That is the resultant. That is what we get if we add these two vectors together. d1 plus d2 equals this dr. We're using the subscript r to designate resultant. So that diagonal line graphically represents the addition of these two vectors. Now we'll get into in the next few slides how to actually mathematically add these and find out what is the magnitude and what is the direction of this vector. But as you can see here from the image I've got here, it has to do with the Pythagorean theorem. So these two vectors with their resultant, the three of these vectors, form a right triangle. Here's the right angle down here. The side opposite the right angle is the hypotenuse. And Pythagoras said that the magnitude of the hypotenuse, c squared, is equal to the sum of squares of the other two sides. So a squared plus b squared equals c squared. So we can use that, the Pythagorean theorem, if we know the magnitudes of these two vectors, to find the magnitude of the resultant. We can also use some trigonometry to find this angle theta, which we will use to describe the direction of the resultant. So here we have basically the same example here. We have d1, d2. d1 is horizontal and 10 units long. d2 is 5 units long. Looks like our units are kilometers here. So 5 kilometers. And we want to add them together. How would we do that? So we have them arranged to make a right triangle. Here's the right angle. So the magnitude of the resultant is the hypotenuse. And so to find the magnitude of the hypotenuse, we would use the Pythagorean theorem. So dr is going to be equal to the square root of d1 squared plus d2 squared. And then if we want to find the angle that it makes with the x-axis, we have to remember from trigonometry class, SOHCAHTOA. The TOA means that the tangent of an angle is equal to the opposite side over the adjacent side. So the opposite side, I know we're looking at this angle right here, but that's the same as this angle here by the alternate interior angle theorem. Or we could think of it taking d2 and moving that over here. I could put d2 over here on this side and take d1 and move it down here. Still keeping its same direction, not changing its angle. We're just sliding it straight down. So there's d1, there's d2. Here's our angle. The opposite side from the angle, the opposite side is d2. And the adjacent side next to the angle is d1. So tangent of the angle is equal to d2 over d1. That's what it says right here. And if we want to get theta by itself, then we need to take the inverse tangent of both sides of this equation. Theta is equal to the inverse tangent of d2 over d1. So using trigonometry, the definition of tangent, as well as Pythagorean theorem, we can find the magnitude and direction of the resultant of these two vectors, d1 and d2. Let's take a look now at what graphically it would look like if we wanted to add two vectors that are not perpendicular to each other. So we have here v1 that's going up and to the right, and we have v2 that's going straight down. So this method of visualizing, and actually we also have v3 here that's going over to the left. This method of visualizing the addition of vectors is called the tail to tip, or I tend to say tip to tail method. And basically all you do is you take these three vectors, you can kind of slide them and move them around so long as you don't change their direction. As long as v1 is still going up and to the right, v2 is still going straight down, v3 is going straight to the left, we can move them in such a way that the tip of v1 and the tail of v2 connect with each other. and then the tip of V2 will connect to the tail of V3, and what we end up with is something like this over here. We have this starting point. We're going to start. V1 is going to go up and to the right. Okay, and then where that ends, we're going to tack on V2. We're going to connect the tip to tail of these two vectors. V2 is going to come straight down to here. And then V3 is straight over to the left, connecting its tail to the tip of V2. And it comes back to this point. So we have a starting point and an ending point right here. Graphically, what we're doing when we are adding these three vectors together is we're saying, okay, we have this starting point, we have this ending point. Forget about this long circuitous path. If we don't want to go all the way up here and down and over, we just want to go directly from the starting point to the ending point. How far is that and in what direction? Okay, so this magnitude, this vector, rather, right here, we would want to find its length and its direction, and that would be the resultant. And I've got some animation here to show V1, V2, V3, and we add them all up, and that gives us a resultant. Another method of visualizing the addition of vectors that I'm not as much a fan of, I like the tail to tip method, is the parallelogram method. So essentially that is, instead of connecting the tips and the tails, we connect their tails. We have the same starting point for each of them. So we've got V1, and then we've got V2, and they're both originating from the same starting point. If we were to come over to the tip of V1 and draw a line, I'm going to draw a dash that's parallel to V2, and then we do the same thing over here. We come to the tip of V2 and we draw a dashed line that's parallel to V1. We end up with a parallelogram. The resultant of these two vectors is the diagonal distance from corner to corner of that parallelogram. Just make sure that the diagonal that you're measuring includes the shared starting point here. So it's not from tip to tip. That's not right. That's incorrect. This is the correct parallelogram method of visualizing the addition of these two vectors. They both start at the same starting point, and the diagonal, the resultant, also shares that same starting point. So this is just a way to kind of visualize and understand what's going on. Again, my preferred method is the tail to tip method. A few more things about vectors. You can make a vector negative. When you make a vector negative, if we just simply flip the sign from a positive v to a negative v here, the direction is going to stay the same, the angle that this is at, the magnitude or the length of it is going to be the same. It's just the direction that changes. So if we want to subtract rather than add vectors, the way we do it is by adding the negative vector. So I've got an example down here. We have V2 that's going up and to the right, and we want to subtract from it V1, which is going horizontally to the right. How do we do that? How do we subtract a vector? Well, we start with the same V2 vector, but then what we do is we add the negative of the vector. So instead of subtracting V1, we add negative V1. So we flip the direction. Now it's going to the left. And so we start with this V2. We go up and to the right. And then we add to it the negative V1, which is going to the left. So we end up with the starting point and this ending point. And the resultant will be the vector that goes in a straight line from the starting point to the ending point. So V2 minus V1 is this vector right here.